I welcome you all for the post inaugural session. Again, it's once again a privilege to introduce the chief guest for the session who's going to take up, Dr. Prasenjit Sen. So he's working as an associate professor at Indian Institute of Science. Prasenjit Sen is an accomplished design and development engineer specializing in MEMS device design, process development, and metrology techniques for failure analysis. With extensive experience in MEMS technologies, he focuses on design and process optimization to improve production yield. His expertise includes the photolithography using steppers and contact aligners, deposition techniques like evaporation, sputtering, LPCVD, PECVD, and all the processes that are involved in the semiconductor. He also has an experience in vapor level packaging using eutectic bonding, frit bonding, and thermocompressing bonding. Prasenjit has a strong background in metrology utilizing tools such as SEM, FIB, and semiconductor parameter analyzers. Proficient in NI LabVIEW, C++, Java, and so on and so forth. Currently an associate professor at IISc, he has been with the institution for over 12 years, previously serving as an assistant professor before joining IISc. He worked at Innovative Microtechnology as a program manager and process development engineer, leading process improvements and wafer level technology innovations. He also served as a postdoctoral scholar at UCLA, USA, developing liquid bearing supported rotary microstages and biosensors for droplet-based microfluidics. He holds a PhD in MEMS from University of California, Los Angeles, and a BTech in Manufacturing Science and Engineering from IIT Kharagpur. Fluent in Hindi, Bengali, and English, Prasenjit has published research on dynamic contact angles and hysteresis in electrowetting on dielectric applications. Sir, it's our pleasure, and I welcome you once again, and we are eager to hear you, sir. Thank you. Extra slide. You can just delete it. Power is okay? Yeah, it's a C type, right? It's okay. Yeah, power is fine. So you have all multiple. That's good. That's good. All right. Good afternoon, everyone. Thank you for that kind introduction. I am Prashanjit, and today I'm going to talk about advanced packaging, and we will start with fundamentals of packaging, what is happening in packaging, what are the current trends, and then we'll talk about finally what is the future of packaging and how it enables how it is enabling the systems that we see today. So before we go into advanced packaging, the first question that we want to ask is, what is packaging? Why worry about packaging? So whatever devices you think about, right? Any kind of device that you think about, whether it's a semiconductor or a MEMS device, that device
needs to be packaged so that it can operate optimally, right? It can perform under its optimum environment and can give the best performance that it is designed for. Okay, and the other aspect is, so the first aspect is the protection. It needs a protection or an environment that it and a device can optimally perform in. The second aspect is a individual device is often not sufficient for formation of systems. So if I look into a cell phone is a system. A system is something that we interact with. Now, a system is never ever created using a single device. There will be a multitude of devices which will function together to form a system. Now, how do we connect these different devices to form a system is also a part of packaging. So packaging basically talks about the device protection and interconnection to give it to turn an individual device into a meaningful section. As you will see, it is a very, very interdisciplinary research area where a lot of effort is going on in mechanical engineering, materials, electrical design, fabrication processes. So there are chemical engineering per se, and there are a lot of other areas also which get involved in packaging. So if you look into a packaging team for any industry, it will have experts from a wide area of background. So let's look into the packaging process flow. So what you see here, uh, so what you see here is essentially the process flow, or the flow in which a device gets converted into a final system assembly. So in the device, first, what will happen is we will design our chips or devices, individual devices. These devices are then fabricated onto a substrate, which is almost always a wafer. The wafer is then diced into smaller pieces, which form the devices. Then these devices are again assembled on a chip carrier or a substrate. They are electrically connected outside. Then they are again integrated into a plastic circuit board to form a board with devices, and then that is finally assembled into a system. So this is a generic process flow that is followed. So you start with a wafer where your devices are designed and fabricated. Then the wafer is diced or broken into smaller pieces to get the individual devices out. Now you will have, for each device, you will have multiple wafers, and they will be singulated, and then these devices or the chips will be integrated, packaged individually, and then integrated into a system, right? So by keeping this in mind, let's try to answer what does exactly the package do, right? And as I was saying even in before, a package, my primary function is to protect and to serve. So what does it mean by protection? First is when I make a device, let's say I am making a microprocessor, right? It is be made on a silicon device. Now that silicon device by itself is very fragile in nature. Why it is fragile in nature? Because it is a brittle material, so it can fall and break. Secondly, it is sensitive to lot of static electricity and other environmental conditions where the environment can actually damage the device. So it needs a mechanical protection from physical damage, where during handling or during operation, the device should not get physically damaged. And that is why we want to put some mechanical protection into the device. Then there is a condition of environment protection. So moisture will affect your device. So if you have open metals, they can get corroded. If you have oxides or other materials, they can accumulate static charge. There can be corrosion also due to the environmental factors. So environmental protection is also very important. If we talk about MEMS devices will also have moving structures, structures which are free to move. So in that case, what happens is, if I am operating in this open environment, that device, any particle which is there in the environment can come and settle down onto that device. Once it settles down onto the device, it can prevent the movement of the particular free structure that is expected to be moving in the MEMS device. And that if that happens, then the device will not function. So environmental protection is also a very important factor when we talk about packaging. Then thermal protection is again another aspect. All our devices will generate heat, and how effectively we are able to take the heat away from the device basically tells us how much power we can push through that device, because all the devices will have a maximum temperature up to which they can function, and beyond that temperature the devices will not function anymore. So to be able to push more power while keeping the device temperature below the critical temperature is also an important part of the thermal of the package. So it does the thermal protection. So this, all the top three parts are basically in terms of protection, different types of protection. But it also needs to provide electrical connection. So if I have a processors and if I have a memory chip, and if they don't both need to talk to each other, there need to be electrical connection that makes the connection between them. Now, why it, so what is so hard about this making the electrical connection? The fact that the today's chips are operating in frequencies which are ever increasing, right? The frequencies are going upwards of gigahertz or multiples of gigahertz. That essentially means that talking between the chips, or the electrical lines which allow the two chips to talk with each other, they also need to be designed accordingly, and they need to be able to take the signal from one chip to the other chip faithfully. Again, President Afkant was talking about today's chips taking a lot of power, individual power, right? So power delivery is again a big challenge in the devices. Now you're thinking about a small chip which is consuming upwards of a kilowatt, right? Now, how do you bring that much amount of power into the chip is also a challenge. It's not very trivial. And it becomes a significant challenge when we are not only talking about a static power, but dynamic power. When certain cores of the processor are suddenly turning on, now your requirement of power might go 50% more. How do you bring hundreds of watts of power suddenly into a chip when your turn on times are in nanoseconds to microseconds, right? So this is also a very big challenge. I don't know how many of you follow, because Intel recently talked about uh, power delivery from the bottom. So they have come up with a platform where they are trying to bring in power from the bottom of the chip rather than the traditional way of bringing in power from the top of the chip. So President Afghan showed in the first slides, he showed the anatomy of a chip, right? He said there are two components. One is the transistor, and then you have the interconnects. Interconnects are the different metal layers which sit on top of these transistor layers and connect different transistors in different fashions. Today's world, having 14 to 15 layers of metal is not very unheard of. It's very common. Now, traditionally, these function of these interconnect layers is to transmit signal between different transistors or different parts of circuits. But these interconnects are also used to bring the power into the chip. So these interconnects were also traditionally used to power the chip. What is happening is, because the way the devices are scaling, the metal lines are scaling, it is becoming harder and harder to bring power from the top of the chip. And that is why what has been looked into is how to bring power from the different part, which is basically come from the bottom of the chip, which has traditionally been never been used before. So powering a device is also a very challenging part in packaging. And then finally, it is to provide the optimum environment for optimum performance. MEMS devices like resonators, right? Uh, for all electronic devices or digital electronic devices, we need a clock, right? Traditionally, a clock is made out of a crystal, but today that crystal clock is progressively being getting replaced by a MEMS based clock, where you have a mechanical structure which is resonating at a very high frequency, and that is forming the clock of the digital circuit. But why a MEMS structure based clock? Because in comparison to crystal, a MEMS clock is much more energy efficient and can be significantly smaller. So that basically means that for applications like cell phones, where your battery life is very important and you want to say save power, these kind of devices become very important. Now, a MEMS resonator is a MEMS structure. It's a physical beam which is resonating at megahertz. And as I was saying, if I don't provide it an optimum environment, in this case, the optimum environment for a MEMS resonator will be a vacuum. If we don't provide a vacuum, then the MEMS resonator will not be able to operate at low power requirements. It will dissipate a lot of power because of the viscous dissipation that is happening because of the moving beam in the air. Okay. So we will look into all of these factors and see how packaging technology has evolved over time. Uh, uh, Okay. So again, to bring this is the anatomy of a standard package, and this will help us in discussing further. So devices are the ones which we make in a semiconductor fab. These are the silicon based devices, if we consider that. Then they are assembled, almost always assembled on something called a substrate package, or which has a redistribution function. Redistribution basically means it takes the electrical connections that are coming out from the device and redistributes in a certain manner which is more adaptable for the system board or the printed circuit board. So the bottom here, the system board, is the one that we normally work with. The substrate is almost always inside a package. Now what is interesting here is if you look at the pitch size, what is the pitch size? Sorry. The pitch size is essentially the distance between the two electrical pads on your device. So if you have let's say a device 1, this is a microprocessor, let's say, then on the microprocessor there will be multiple pads through which your electrical connections will come out. Now whatever the number of, so these pads will be spaced at a minimum distance. Now this pitch turns out to be approximately 80 microns for an example. So this will be in the tens of micron scale. Now the system boards that we work with, which are primarily the printed circuit boards, in this case the pitch will be in the order of hundreds of microns, couple of hundreds of microns. Now, one of the functions of this package is to be able to make this connection from the small pitch size to the large pitch size on the board. So the package function is also to resize the interconnect pitches because there are mismatch in the technology, right? So our printed circuit boards are at a much larger pitch sizes and feature sizes, whereas the chip is progressively becoming smaller and smaller, and the pitch sizes and the pad sizes on the chip are becoming smaller and smaller. So now if I have to connect this device to the board, I also need a intermediate layer, and that is what the package substrate is also doing. Again, so this is something I have discussed. Skip this. So what is the need for advanced packaging? If you have paid attention, even in the ISM, there are 4 sectors which are getting funded, and one of the sectors is in the packaging sector. So why this push towards advanced packaging and why this worry? So one of the aspect of Moore's law was discussed, so I will not go that, but there are 2 aspects of Moore's law. First aspect is the reduction in the size of the nodes or the size of the transistors, and doubling the number of transistors in a particular given chip. The second aspect of the Moore's law is also the reduction of the cost. So cost per transistor is also expected to go down with the increase in the number of transistors, because if the cost doesn't go down, then every next generation of your device or your processor is going to be more and more expensive in comparison to the previous generation. Now what is happening today is, if you look at the cost for the newer nodes is not going down. They are more expensive in comparison to the previous generations, and that is a limitation in the Moore's law. So your chips will not become progressively more, you will not get more transistors for the same cost. Your cost is also going to go up. And this is what is happening progressively with newer and newer generations of nodes. So then what is the thought? The thought that is there is today is that, do we really need to make all these sections of a system on the lowest node size or not? As again, Navkant was talking about the system on a chip, where he showed the Xilinx platform, where he said you have field programmable chips, you have ADCs, you have communication chips, you have the processors, multi-core processors, all of them assembled or integrated in a single platform. Now the question is, do we need to make all of these devices using the same node or not? And the answer is no, it is not required to make all the devices using the same node technology. So if my latest technology node is 3 nanometers, everything does not need to be made out of 3 nanometer node. Only the most critical part, where that performance benefit will help us, is the part that needs to be made out of 3 nanometers. There are certain parts of the components which are much better made using a 45 nanometer node or a 28 nanometer node. So from there, the idea is coming that, or what the idea has emerged, is that rather than making one big chip which has a lot of different functionality, you essentially make smaller chips which have the different functionalities that you require, and then you integrate them closely to get that functionality. So for example, in that same Everest platform, uh, the FPGA element and the processor element could be made out of the smallest node size that is available. But the transceiver modules can be made out of nodes which are significantly larger in size, and that will give you a more optimum performance. But if you have different technology nodes coming together, you cannot fabricate them together. So what you do is you fabricate these small pieces separately, and then they are co-integrated together in a small fashion, right? And this is what the future is, or what the future is being predicted to be, where people are talking about, rather than large chips or large ICs, people are talking about large packages, where in individual package you will have a large number of dies which are integrated uh, on integrated to give a high functionality, very high performance and low cost. How is it different from a printed circuit board? The difference is, when we do the electrical scaling of the interconnects, as we talked about in the last slide, we are taking it from a smaller line size to a larger line width, and then going on the printed circuit board, and then going to back to the chip, right? We are talking about this figure where you have a smaller interconnect, smaller line width or smaller metal lines. Then you have become larger line widths. From this larger line width, you will go to the next package substrate through a larger line width, and then from there you will go to a smaller line width. The problem is, if I do this, I can only have a fixed number of electrical lines connecting the two chips, because on the board my line width is very large, right? So given an area, I will not be able to connect larger number of pins from device 1 to device 2, and that is a problem, because if I cannot put larger number of interconnects, my speed at which I will talk between the two chips is going to get limited. I have limited number of lines. Frequency is fixed, so I cannot transmit data at above a certain rate. If I can increase the number of lines or electrical lines connecting the two chips to 2 times, my data rate can become 2 times. So why we cannot do the same thing what is being projected here using the packages? Because traditional printed circuit boards have very large wires which limit the number of connections that two chips can have. And that limits the speed at which these two processors or the two parts of the system can talk to each other. Okay, so that is where this large package idea, where chips are interconnected but interconnected at line widths which are very small as the line widths that you see on your devices, then we can have a very large number of connections and we can have a very large bandwidth between the two devices. Okay, so what are challenges? There are multiple challenges in packaging. So this is a high performance board, and what I was talking about is a big challenge in the sense that what Navkant was also talking about, right? The von Neumann bottleneck, right? The main bottleneck today between von Neumann architect in the architecture is you have a processor and you have a data, and this data has to be moved to the processor. Some processing has to happen, and then the data has to move back to the data storage part. And that essentially means the speed at which we can process data is essentially getting bottlenecked by the speed at which we can access the data in the processor. So now if I have to design a, a, a system like this where you have multiple different levels of memory for storage of data. Why do we have multiple different stages? It's because of the cost factor. So L1 RAM is normally the cache which is closest to the processor, right? But I cannot make all my memory out of that kind of memory because that memory is very expensive. So then what happens is then you have the L2 which is slightly slower but is a lower cost. As we trade between cost and speed, you will have different levels of memory with different amounts of storage capacity. And how do we place these memories and how do we interconnect these memories so that we can get an optimum system performance is a packaging challenge. When we look into consumer packages, there is a very different level of problem. In these kind of packages, which are essentially present in cell phones and smartwatches, we do have the performance challenge, but at the same time, we are also struggling with space. So in this case, how do you package multiple devices or multiple devices into a small space is also a big challenge. In biomedical devices, in addition to the traditional packaging challenges, we also face challenges because of biocompatibility. So this is a cardiac pacemaker which will have electronics into it, a battery into it, and this will be placed inside a human heart. Now the packaging challenge here is this material has to be biocompatible, or the whole package has to be biocompatible So with this, I'll stop and thank you for taking the time.
Thank you for the wonderful session by the professor. Uh, Professor had given the deep insight into the packaging technology with the following topics like introduction to advanced packaging, the packaging flow, the the process delivery, the future, then also the challenges which are involved in the interconnects, packaging and integration. So different types of integration levels, then the wafer level packaging and hybrid bonding, and finally concluded that how the interconnects we can scale down not only to the particularly the interconnect but to the whole system. Thank you for your wonderful session, sir. I request our HOD and also the the coordinators to honor the speaker.